Hi, welcome to this lesson on Euclidean geometry, the proportionality theorem. Let's have a look at question 6. So we're given a triangle ABC and we're given all that information. So X is a point on BC, right? And N is a midpoint of this line AX, Y is the midpoint of this line AB, and M is the midpoint of this line BX. Okay, we want to prove that MR, so this distance here, is equal to a half the distance of BC, which is this distance here. Okay, so let's see how we can try and prove this. So let's get a proof out. So again, because I see multiple triangles, some parallel lines, some midpoints, we're most likely going to have to use a combination of the proportionality theorem or the midpoint theorem here. So because I'm looking for MR, I see MR relies on two different things. It relies on this mx part here, and it relies on this xr part here. So if I can try and work with those values in some sort of proportion, then I can try and relate it to this bigger part here, this BC part here. So just to make my life a bit easier, I'm going to assign some variables here so I can see the picture a bit better. So what I'm going to do is I'm going to let the length mx equal t. Okay, so therefore bm equals t as well. That was given information to us. And then I'm going to let the distance of xr, let's call that q, for example. Okay, so if I can just figure out the length of rc, then I can work out things in terms of t and q here, and hopefully show that mr, right, which is in this case t plus q, is equal to half of BC. So that'll hopefully give us half of T plus Q. All right, so let's go ahead and check that out. So first of all, I'm going to say let mx, which is equal to bm, right, because m is a midpoint, equal t, and let xr equals q. So I'm just telling whoever's reading my work exactly my train of thought and logic that I'm using. Okay, so now I notice that these are parallel lines, and this point R goes to a midpoint N on that line. So I can say in triangle AXC, so AXC, R goes to the midpoint N on AX, and we were also given in the diagram NR is parallel to AC. So therefore, by the converse of the midpoint theorem, right, the converse of the midpoint theorem tells us then that, therefore by the converse of the midpoint theorem, we have R is a midpoint of XC. Okay, so if you have a line, a point that goes to another midpoint, goes to a midpoint on the opposite side, and the lines are parallel, then by the converse of the midpoint theorem, R must be a midpoint of XC. So therefore, this implies then that XR equals RC, because it's a midpoint. But we know XR, we called it Q, so that must be Q as well. So now let's see what we have here as our conclusion. So therefore, MR, so this distance here is T plus Q on how we've defined it. And half of BC, that's equal to a half times. So BC is essentially these four lines added together. So it's a half of T plus Q plus Q. But that's half of T plus T is 2T, Q plus Q is 2Q. So if I distribute that half of 2T is 1T, and half of 2Q is 1Q. So therefore, I've shown rigorously that MR is exactly equal to half BC. All right, so to summarize, what we had to use here was the fact of the converse of the midpoint theorem, which tells us that if a point goes to the opposite side of the triangle to that midpoint, and that line is parallel to the third side, then that point must be a midpoint of that line XC. Using that, I was able to fill in the rest of the missing information and therefore just work out the lengths using that information I've assigned. All right, so again, our algebraic toolkit came into play here. The geometry toolkit came into play here with the proportionality and midpoint theorems, and therefore we were able to show that this result is true. Awesome. I'll see you in the next one.